Now let's take a look at example number 3. We want to show that this series, this infinite addition problem, is convergent and ultimately find its sum. Well, to do this, we're going to see that finding our partial sums, finding our s sub n that we had talked about in the last video is going to be extremely important. But in order to do that, we're going to start by performing a very kind of strange and awkward move that's maybe a bit unexpected. Here's what I'm going to start with. I'll start by saying that using partial fractions, we can rewrite 1 over k times k plus 1 into, remember how this would work. This would be like an a over a k plus a b over a k plus 1. And I'm going to go ahead and skip a lot of the work here. You can check this work up on Blackboard with the notes that are posted there, or work through it on your own. But I believe that you can work this all the way down to the following. I think it's possible to rewrite this starting fraction as the sum of these two other fractions. Now again, this might seem like a completely weird and out of left field sort of a move, but there's a good reason for why we want to do it. So I can state that if I have an addition problem that looks like this, we've now said that we could rewrite this as an addition problem that has the shape 1 over k, and I'll just write this as minus a 1 over a k plus 1. Now, again, I could start to try to find my S1, my S2, my S3, kind of like what we did in this last example. But if those numbers don't turn into some like apparently alternating or oscillating sort of a sequence, then I'm really going to be stuck in finding my limit. So again, I'm trying to find a formula for our S sub n. And this separation here into these two fractions, I believe, is really going to help me. So I'll state here that we then calculate that the sum of the first n items out of this list, well, I can't come up with a formula immediately, but at least I could start to write down what that would look like. So let's imagine what it would look like if I went to this set of parentheses over here, and I started just again adding together these different sets of parentheses, right? So like I plug in a 1, and that would be like plugging a 1 in here for k. It's the first item. Notice that would get me 1 minus 1/2. That's the first set of parentheses. Now I'm not even going to go ahead and simplify that down at the moment. I know that I could, but I'm not going to. Instead, I'm going to go ahead and figure out what would happen with the second set of parentheses. Again, I want to take the sum of the first n items, and so far I'm going to have the first 2. Notice that the second item would be when I plug in 2 for k, so that would look like this. Then I'm going to write down the third item. Notice that's going to look like this. I could write down the fourth item. That would be when k is the number 4, and that's going to look like this. And I would have to keep going and going and going, not forever, but up until I get to thing number n. Well, notice if I go to thing number n, that's going to be 1 over n minus 1 over n plus 1. That's what I'm going to have. Now, this is not really a great formula for S sub n, those partial sums, because, I mean, when I look at this isn't like something easy to work with, because it's got this dot, dot, dot. But you may notice that there's an interesting sort of a pattern that goes on. I don't really need these parentheses, right? I could totally drop them out. And if I do, I could notice that I'm going to have a negative 1/2 right here. That's going to cancel with this positive 1/2. This negative 1/3 is going to cancel with that positive 1/3. That negative 1/4 is going to cancel with that positive 1/4. Notice you can almost see the pattern that if you're working with a number that's at the back of a set of parentheses, it always cancels with the front of the next set. So notice, like negative 1/5, well, that would cancel with the front of the next set of parentheses that would be coming in the dot, dot, dot. Notice that numbers that are at the back, or at the front, of a set of parentheses always cancel with the thing that kind of comes right before it. So like this 1 over n would actually cancel with the set of parentheses that comes right before it. But notice there's nothing that 1 cancels with. And again, if the back of the parentheses always cancels with what comes next, clearly this 1 over n plus 1 is not going to cancel with anything. And so ultimately, I can get to that this really simplifies to be the following. And notice then, I have a formula. This formula should tell me, when I plug in a value of n, the sum of the first n items out of this addition problem. We can actually test it out, right? Like, let's see quickly here what this addition problem actually looks like. Notice, if I plug in the number 1 here, I'm going to get a 1/2. If I plug in the number 2, I'm going to get a, what is that, a 1/6. If I plug in a 3, I'm going to get a 1/12, and so on. Well, notice, if I was to say I wanted to add up the first item in the list, I would just get a number 1/2. That's what this formula can find for me. To find S number 1, I would plug in a 1. And notice that gets me 1 minus a half. That gets me a half. Notice that if I took a half and a sixth, the first two things, and I added them together, that would be like saying 3/6 plus 1/6. That should be a total of 4/6 or 2/3. And the number 2/3 will pop out of here if I simply plug in the value of 2. Notice if I plug in a 2, I'm going to get 1 minus 1/3, which is 2/3. So this is a formula that tells me the running total of this series. This is awesome. Like, this idea is really, really powerful. So now that I have this awesome canceling that goes on, and I have a formula for S sub n, I can easily calculate the limit. So I'll say we calculate the limit as n, the number of items that I'm adding together, goes off to infinity. And when I do that, that means I'm calculating the limit as n approaches infinity of 1 minus 1 over n plus 1. Clearly that's going to be 1 minus 0, because the denominator here is just going to get larger and larger and larger. And so this results in 1. And so now that I know that my green S sub n converges to 1, by definition, we can then say that the original series is going to converge, and it converges to 1. So this series does indeed converge. It adds up to 1. So this is a really, really convenient thing that we're able to do at times, which is this kind of large canceling process. This idea of canceling all these kind of different terms here and being able to generate a formula for this S sub n means that we're going to be actually choosing to give a name to a series that kind of operates this way, that has this sort of canceling behavior. And we refer to this type of series as a telescoping series. It's one where I get this kind of canceling to happen when I write out my S sub n's. Now, this may not always be the case. In fact, this is very often rarely the case, but in the event that it can be done, it provides us with a nice way to determine if a series converges or diverges. You can then kind of see here why it was maybe important at the start of this problem to take the given fraction that I had and separate it into two fractions. If I have the ability to have an item minus another item, there's a good chance I might be able to get some things to cancel out when I write out my partial sums. So I won't always need to use partial fractions on questions like these, but sometimes it can be useful.